Alright, let's begin. We know that the files exist in /Narnia, so let's see this. We know that we have already solved these things, so we don't need that, but this one. So these are the two files that we need to care about right now, okay? Narnia 2 binary and Narnia 2.c. Okay, so before jumping in, let's see what this Narnia 2.c has, okay? So this is the main function, and it accepts some argument, and it has a buffer that is set to 128 characters. Okay, if argc equals to 1, which means if no argument exists, then it's gonna print this usage and then exit. But if some argument exists, then it's gonna just take that argument, put it inside this buff, which is this one, and then it is going to print that buff, okay, and then it's going to return 0. So where do you think is the problem in this code? Okay, so this is the line that is problematic because there is no limit of how much buffer it can take. Okay, but here there is limit, but it doesn't matter. This is the one that is vulnerable. Okay, so let's try and execute Narnia 2. Okay, it expects an argument. Let's give an argument, and then that is being returned over here. Let's see if we can give a bigger argument, because we know that it expects at least 128. Okay, so we need to give more than this. Okay, let's copy that, and let's say there is a shell in which I'm going to execute Python. So there is no Python actually. Okay, so let me show you what I mean. Python. Okay, there's no Python, so we have to say Python 3. Okay, so Python 3 exists, so we need to give a Python 3 syntax. Okay, so you say Narnia. Okay, so let's do the Python 3 syntax and then we'll see Narnia. Okay, so Python 3 and then -c print, you can say 128 times capital A. Okay, and then end it with this. Okay, so now you can see that you can execute this code, right? We use that same thing with Narnia. Okay, so let's say Narnia 2 and then this, but this needs to be enclosed in a subshell. Okay, so let's see what happens. Okay, so it is able to give us our data back. So let's go back and change it. Let's change it to 4 and let's execute. You can see that it is segmentation fault, which means this data is too much for it to handle. Okay, so let's give a little bit less data. Let's say 135. Still segmentation fault. Let's say 130. Okay, it's able to give 130. Okay, so we're getting close. 132 and segmentation fault. So we're getting really close. Now let's say 131. Okay, so 131 is okay, but 132 is causing an error. So let's see what happens at the memory level. Okay, so let's see Narnia 2, and before that you can just say that open quietly. Okay, let's copy this Python script and let's hit enter. And let's say yes. Once we are in GDB, let's say disassemble main, and then it just disassembles the whole main. So we know that initial printf is not necessary because it's just checking if any arguments are there or not. But this one is actually copying it and then printing it back. Okay, so let's give it somewhere around here. Okay, so let's hold it here and then we'll examine everything else. Okay, so let's say break at main plus 81. So that's what it means, right? Main plus 81. So this is where we want a breakpoint. As you can see, this address and this address are same. We have established a breakpoint right here, and then we want to run this an argument something like this. Okay, so let's see what happens. So it executed and it stopped at the breakpoint 1. Let's see if it exits normally or not. Okay, but we know that it exits normally, so let's continue. by pressing C, and it exited normally. Okay, let me do the same thing again, but this time let's give 32. Okay, 132. Let's continue, and you can see that it's causing a segmentation fault. So let's keep doing this, and let's see what happens if we just increase some more data. Okay, so let's continue. Okay, so this time we're getting a new error over here. Okay, so we did not get this previously. Okay, so as you can see, we didn't get that previously, but this time we actually got a different kind of error. So this is basically return address, something like if something goes wrong, go to this address. In this case, let's try to examine some stack pointer with 50 words of memory from stack pointer. Okay, so let's do that in reverse. Okay, you can say reverse means if you said from down up, not from up down. So let's see what happens. So your A is actually starting from here and ending right here. Okay, the return address has 0x414141 somewhere, we don't know. Okay, so let's do one thing, and let's change this to, let's say, some bytes. Let's say 131 plus 4 times B. Okay, so let's say B. We have to find out where it actually returns this address. Okay, so let's say yes, and then continue, and as you can see, one more byte needs to be pushed. Okay, so here let's keep 132A, and now let's run it and continue. As you can see, we have replaced the return address with 42424242. Okay, if we make this return address pointing to a shell code, then we probably can get a shell, right? So let's find a shell. So we have used this shell previously, but this is of no use, but we'll just tell you why we can use this. So replace this with shell code and say print some bytes, and then after that bytes, let's give a return address. So we don't know the exact return address, right? So let's try to find that return address. Okay, so let's give 50. I think 50 should be enough. Okay, so the code starts from this area. Okay, so let's give this memory code in here plus double quotes again, \x this, and then \x this, and then \xff okay, so this is the return address. This is where it has to return to. Okay, and in between, okay, so this is the shell code we're executing, right? And then we have to add some data here. Okay, so this data has to be such that if you add all of these bytes and this bytes and the data which you're going to input, so it should be added to 136, because that's what we have inputted here, right? 132 plus 4, 136. Okay, so you need to make this whole thing into 136 bytes. Okay, so we already know that this shell code is 23 bytes. Okay, so what you can do is you can say 132 minus 23 and multiply it by some random character, let's say A. Okay, and then add this at the end. Okay, so this will be your shell code. Let's see if this one works. If this doesn't work, then we have to follow some other way. Let's see, run, enter, and then let's continue. So as you can see, it is just pointing to 41414141. Okay, which is not what we expected. This particular return address that we have given is again pointing to a different address. Okay, so we don't want this to be executed as a part of this. Okay, so what we want is for this shell code to execute. Okay, so we don't know exactly where that is, so we need to say examine 50 words of memory and then at stack pointer. So here you can see 50 words of memory from stack pointer starting from here. Okay, so here you can say 41414141, and then above this there should be more data. Okay, so let's give 250. Okay, let's see all the data that is there. So it's again starting from here. Okay, it's saying that this is the thing, and from here there are lots of other data, and let's keep going, and as you can see we have more of 41414141 data here. Okay, so where did this come from, right? Let's do one thing. Let's give something like a NOP sled. So if you see this code, we have given shell code in the beginning and then some random characters. Then we are giving a location in memory, so where it is going to go and check for certain code. Okay, so we're going to slightly change this, and let's say we're going to give the same shell, but this one has to be in the beginning. Okay, so and say plus, but this one has to be NOP sled. Okay, so whenever whenever the program detects hex code 90, it is simply going to ignore that hex code. Okay, so by ignoring, we are saying that it is no operation hex code, so that is called NOP. Okay, so when we give these many NOP characters, we are basically going to say somewhere in middle of these hex code 90, which is NOP, if you reference it, it is going to just come down to the shell code, and then this shell code will actually execute. Okay, so let's try this and let's see what happens. Okay, so here we also need to take care of the location in memory, but currently we're just gonna paste it and let's see what happens. Okay, so when you execute that, so you hit a breakpoint and let's continue, and here you got a different hex code. Okay, so looks like you cannot use Python in this case. So let's see the stack pointer. So there are lots of these things, but it wouldn't matter. Okay, look at this. So we're getting lots of these characters, but it is not hex 90. So we need to have a different kind of payload over here. Okay, so instead of using Python, let's use something like echo or printf or something like that. Okay, so to do that, you have to type all the characters. Okay, so something like this. So you have to type 136 characters, which includes this no operation characters, and then the shell code, and then this reference where we are referring to. Okay, so we know that the reference is D248, and let's see what happens. Let's begin from the beginning. Let's continue. Okay, so we have a different reference point this time. Okay, so let's see what happened in the stack pointer. Okay, so here let's continue. Okay, look at this. Here we got all this NOP sled, right? So let's pick somewhere in between so that it will just come down and execute this shell code. Okay, so something like this. So let's give some reference. Let's say 54. Okay, D554. Okay, so just go back to the payload and keep that it is D5 and 54. So D5 and 54. Okay, cool. We are saying whenever this code finishes, let's go to this location, and then this location is this location, and then it is going to just slide down to the shell code, and the shell code will execute and it will pop up a shell. Okay, so let's see if we are correct. Okay, so let's continue, and look what we got. We got a shell, right? So let's use the same payload outside GDB. Okay, so let's exit out of here and exit out of here as well. Okay, so you're gonna say Narnia 2 and then give this shell code, and once you hit enter, you pop up the shell. So let's type who am I, and you're still Narnia 2, you're not Narnia 3. Okay, so which means you have to use a shell code that has -p in it. Okay, something like, it preserves effective user ID of Narnia 2. Okay, not the real user ID, which is Narnia 2, but effective user ID of Narnia 2 is Narnia 3. Okay, so let's exit out of here. Let's build our new payload. Let's go to the browser, and we know that 606 has this bash-p. Okay, so which means it will take care of all the privileges and give effective user ID. Okay, not the real user ID. So we'll just copy this and paste it, and let's say shift tab, shift tab, shift tab. Okay, so let's remove this and remove this and remove this, and now we have shell code. Okay, so this is 33 bytes. Okay, let's open up calculator. So 132 minus 33 bytes. Okay, so it's 99. So we need 99 bytes of NOP sled. Okay, let's say string counter. So we need so many hex 90. So this is 5, and then we got 10, and then we need to say 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so we need to remove this last one so that it is 99. Okay, so now we have 99 no operation characters, followed by this and followed by the return address. Okay, so what is the return address? So we know that the return address is this one. So let's copy this and paste it over here. So now the payload is ready. So we need to give this payload to this. Okay, so we're gonna say Narnia 2 and backtick echo -e, and then give this followed by backtick. Okay, so let's see what happens. So now we got a different type of shell. Okay, so hopefully this is not Narnia 2, this is Narnia 3 shell, because as the shell code says, it needs to preserve effective user ID. So who am I? Narnia 3. Let's get etc / Narnia _pass Narnia 3. Okay, so this is how you get your shell. Okay, so clear. I'll tell you where they'll make mistakes. So let's run gdb Narnia 2. So disassemble main and keep some pointer. Let's say break at main plus 81. Okay, so this is all common practice. We already done this. So let's give a payload of 136 characters ending with 42, 42, 42, 42. Okay, so let's see what happens once we do this. Okay, so we have hit a breakpoint over here. So let's continue. Okay, so we have successfully replaced return address to 42424242 words of memory in stack pointer. Okay, so here you can see that it is 42424242 and 414141 and so on. So let's give some more memory. So let's say it is 30. Okay, so now we have some more memory. So let's give 50. So here you can see that it's 248. Okay, so you will think that this is the exact code that actually starts allocating data, right? But this is not the case. If you try to give this data as a return address, then you're actually mistaken. Okay, so if you type 150 or let's say 250 from stack pointer, so let's see what happens. Okay, so this is where we're starting, this is where we keep going, and as you can see, we can see 41414141 from here. Okay, so this address is different, right? So D510, D550 and so on. So if you remember, this is the exact address that we have given. Okay, so D554. So don't confuse with the addresses. Okay, so make sure you try both of them and give ample amount of memory from the stack pointer so that you can identify this data. Okay, so exact memory address of this. Okay, so once you give this address, you're actually able to execute the shell. So I hope you get it, and I'll see you guys in the next one.